Alright, now we are going to study regression and correlation. Regression is a problem where we try to find some dependence of a random variable on other random variables. For example, let's say we have two random variables, okay, x and y, and in regression we tried to find a relationship between x and y in such a way that y is expressed as a function of x. So we try to guess what kind of function this is. Okay, the simplest possible function is a linear function. So in this case, we want to find something like a plus b x or like that. So somehow we want to determine these coefficients, and these coefficients determines this function, linear function. So that's linear regression. And in correlation, we don't assume this kind of functional dependence, but we just uh, consider correlation between, for example, covariance between x and y, or correlation coefficient, which is variance of x, variance of y. So we just treat x and y equally in a sense. So one doesn't not necessarily depend on the other in a functional way, but they just depend equally on each other. So we deal with these two problems in this chapter. First, we are going to study linear regression. Although it's called linear, it can be also applied to nonlinear functions. Let's see one example. In chemistry, we have Arrhenius law. Arrhenius law, which says chemical reaction, the rate of chemical reaction of some chemical reaction is expressed as some constant times exponential of some constant divided by the absolute temperature. So this T is absolute temperature measured in Kelvin. Okay, so this is a positive number, and this is C is a constant. This B is a constant. It's called activation energy. So this is clearly a nonlinear relationship. If you plot this reaction rate, so this is reaction rate, so this is temperature, so this is temperature and reaction rate. So reaction rate is a function of temperature. It's a nonlinear function. So it will. So this is like when t is 0. I mean, t cannot be exactly 0. So when t is 0, this b is positive number. So this exponent becomes negative infinity. So the exponential of negative infinity is 0. Okay, so at absolute temperature of 0, the reaction doesn't proceed at all. And when temperature rises, it will rise like this. But when temperature goes to infinity, this exponent becomes 0. So that is exponential of 0, which is 1. So this reaction rate converges to some constant, which is the C, right? So it will be C times 1, so it will converge to C. So this is clearly a nonlinear function. It's not straight line. It's curved. But if you take logarithm of both sides, we have log k and some constant, which is log of c minus bt. So in this case, if you plot again, let's take t, and instead of k, we plot log k on the vertical axis. So this is, so how how does this function look like? It will look like something like this, right? So when t goes to 0, this part, second term, will be negative infinity, so it will diverge to negative infinity. But when t goes to infinity, this term converges to 0, so it, as a whole, this log k will converge to a. This is actually log of c, right? C is this c. Still, this is a nonlinear function, obviously. However, so we have this log uh, k a minus b over t. But if you plot this function, instead of t, we take 1 over t on the horizontal axis and take log of k on the vertical axis. Then what's the shape of this function? So maybe it's a little bit hard to think about this on the horizontal axis. So maybe you can put, instead of 1 over t, we replaced it with s equal to 1 over t. Then in that case, this is bs. So instead of 1 over t, we put s. So if you look at this function, it's just a linear function. Okay. So this is the intercept is a, and this b is positive, so it's minus b is negative, so the slope is negative. So this is a function, linear function, like something like this. Okay. So by changing the variables, like taking the logarithm or taking the inverse, then sometimes we can make nonlinear relationship into linear relationship, like this. So this is a linear function. This is just a straight line. So therefore, linear regression has more applicability than it seems at first sight. Now let's look at some real examples. This is a chicken, and this part is called the comb of chicken. Okay, so here's our data. Comb growth in capons, so capons means chicken, receiving different doses of androsterone. Okay, this is a kind of hormones. Okay, so if we uh, give this much dose of this hormone, androsterone, so zero point 0.5 milligram, then the comb growth is 8 millimeters in one chicken, and 1 millimeter in another chicken, and 1 millimeter in yet another chicken, and 3 millimeters in yet another chicken, and 1 millimeter in another chicken. And if we increase the dose of this hormone to 1 milligram, then uh, in 5 different chickens, we had these different numbers of comb growth in millimeters, and so on. So we increase the doses, and we get some different values for comb growth depending on individuals. And if we plot, so instead of taking these doses, just instead of the raw values, we take the logarithm of these doses with base 2. Then plot this in a graph. So this is log 2 of dose on the horizontal axis, and this is comb growth in millimeters in y-axis. So we see these points. These are, each point represents an individual chicken. So maybe we see some relationship, right? If we increase the dose, the comb growth will also increase. So there is kind of sort of linear relationship. So our goal here is to find exactly what kind of linear function this is. Okay? In order to decide a linear function, we need to find the intersection and the slope. So there are two parameters to be determined from this data. Okay, first thing you should think about is that this linear relationship, apparent linear relationship, is not exact relationship, right? So, for example, even if you give different chickens the same dose of the hormones, different chickens may grow different sizes of combs. So it's not exact relationship because one independent variable doesn't determine the unique value of the dependent variable. So we should consider these values as random variables. So how do we model this problem? So let y be the random variable representing the comb size. Then what we expect as a relationship between the dose, so x is the dose of androstenedione, so what we expect as a relationship is something like this. So expectation value of y given the dose is given by this formula, alpha plus beta times x. So where alpha and beta are some parameters which are unknown at this moment and which will be never known. These are some idealized parameters of idealized world, of idealized models. So, of course, this is approximate, and no linear function can represent the reality completely accurately. Because think about this. If we increase the dose of x to infinity, do you really expect the comb size to be infinitely big? It's impossible. It should saturate at some point. So this relationship does not hold exactly, and this also it doesn't hold for entire range of x. So this is just approximation for a limited applicability. Anyway, so and we don't know this expectation value actually, but we do know some experimental values of y, some observations. This. So each observation of comb size, we assume this is expressed as some linear function of x plus some errors. So this is error. So this is approximate relationship with some error included. So we assume this equation holds for each data point, right? So in the previous graph, we have each point is represented by x coordinate and y coordinate, right? So for each pair of x and y, we assume this equation should hold with some unknown error. Okay? But the point is, if we determine a and b, then the error is expressed as y minus a plus bx. Okay? So in the end, we assume this error should follow some kind of normal distribution with zero mean and some variance. Okay, so this error is the random variable. Okay, so what we want to do is to minimize this error. So we want to determine a and b as accurately as possible, in the sense that this equation holds as accurately as possible. So how do we do this? So in order to find the values of a and b, we first define this square deviation, sum of square deviation of, well, let's say sum of squared errors. So before this, so let's assume we have a set of pairs of data, x1, y1, x2, y2, x3, y3, and so on up to xn, yn. So these are the pairs of data. For example, in this case, negative 1 and 8 is one pair. Negative 1, 8. And negative 1 and 1 is another pair. And 1 and 13 is another pair. And so on. So in this case, we have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 25 points of data. So in this case, n is 25. So we have this data, and we define this sum of squared errors. So I to n, and we square the error. Okay, so error is defined in this way. So that is yi minus a minus bxi squared. Okay. Why do we have to square this? Well, think about this. If you don't square it, or you could have just done something like this: sum of errors instead of squared errors. What would happen? If we assume this error follows this normal distribution with zero mean, okay, this summation will end up to 0. You should try to prove this. Okay, but that doesn't help us. So, but if we square it, it cannot, some errors may be positive, some errors may be negative, and if you just add all those errors, it will just cancel out. Positive part and negative part will cancel out and give you just 0. But if you square it, it won't cancel. So this has some meaning. It is always positive, right? If you're lucky, it can be 0, but never negative. Okay. So from this, we want to determine, this is a function of a and b. Xi and yi, they are given data, so they have some given values. But a and b, they are unknown, so we treat them as variables. So what we want to do is to minimize this quantity. To minimize this, we differentiate it and find the minimum. So differentiate it with respect to a and b. So if you differentiate this s squared with respect to a, what do you get? So this is, if you differentiate a summation, that is that will be sum of differentiations, right? Sum of derivatives. So you differentiate inside this, you get 2yi minus a minus b xi. So differentiate this part, so it will be negative 1. And you equate this to 0. Okay. And you also differentiate this s squared with respect to b. And this is so similar up to this point. And so by the chain rule, you have negative xi here. So this should be equal to 0. Okay. Now let's manipulate this a little bit. So first, this one. Okay. Since we are equating with 0, so we can just cancel this negative 1 and 2 here. So what we have from the first equation is this yi minus abx, which is sum of yi and minus sum of ia minus sum of bxi. So sum of yi, so what's this? Sum of a constant. So I runs from 1 to n, so this is n a. You know, I've seen many students, this is equal to a, but it's not equal to a, it's equal to na. Okay, and you put this b outside, so we have this. Okay, equal to 0. Now let's divide everything by n. Okay, so everything by n, we have 1 over n sum of y. So this is a and this is b, 1 over n sum of x equal to 0. Okay, but this is just the sample mean of y, so let's put this as y bar, and this is sample mean of x, so let's put this as x bar. So after all, we have y bar minus a minus b x bar equal to 0 from the first equation. Okay. Okay. So actually it is nice to see that, you know, the first the model is actually exact for the averages. On average, it's exact. If you put individual data, there will be an error. But if you just consider the averages, then it looks like, you know, it's exact. Okay, so what about the second equation? What's the second equation? Okay, this one. Let's copy this. Okay, so the second equation is this one. So since this is equal to 0, we just cancel this 2 and this cancel this negative sign. So let's see. If we distribute this, we have the left hand side is equal to xi yi, and we have minus a sum of xi and minus b sum of xi squared equal to 0. Okay. Let's see what we can do now. So we have, let's see, from this, I think we can get rid of a. So this is a equal to y bar minus bx bar. So let's put this a into here. So we get xi yi minus y bar bx bar, sum of x and bx2. Let's see. Okay. So, okay, so why don't we, so this is equal to 0, right? So why don't we just divide everything by n? So this will be n xi yi minus uh, y bar bx bar and n xi and b n of xi squared equal to 0, right? But this is the sample average, a sample mean of x squared. So let's write x squared bar. Okay, so this is not x bar squared. It's different. Okay, x squared bar. And this one is the sample mean of x times y. So why don't we write x y bar? Okay, and this is the sample mean of x. So this is x bar, right? Okay, so to simplify this, we have xy bar, and we have y bar, bx bar, and x bar, minus b, x squared bar. Okay, let's expand this. So we have xy bar and minus x bar times y bar. Okay, so this is different from this one. X bar times y bar is not xy bar. Okay, and let's see, plus b x bar squared and minus b x squared bar. So do you see something familiar here? So this is actually covariance of x and y. Actually, this is sample covariance. And this one, so if you factorize b, this is equal to b x squared bar minus x bar squared. So this is variance of x, right? Oh, okay, this should be a negative sign here. So what we have here is covariance of x and y minus b times variance of x, which should be equal to 0. Okay, so from this we can solve for b, which is covariance of x and y divided by variance of x. Okay, so if you use this b and use this equation, you can determine the value of a. So let's summarize. So the value of b is covariance of x and y divided by variance of x, and the value of a is given by what was it, y bar, so average of y minus b x bar, So if you put this b in here, so you have y bar covariance of x y variance of x times x bar. So these are the optimal coefficients for the linear regression. Okay, now let's consider the same problem from a different angle. So we assume that each data point yi can be related to the value of xi in a linear relationship, alpha plus beta times xi plus some error. Okay, and these alpha and beta are unknown parameters, but we from minimizing the sum of squared errors, we obtain an estimate of alpha as A, estimate of beta as B. So these are estimates. Okay, so now we cast this problem of minimizing the sum of squared error as a maximum likelihood method. So since epsilon I follows normal distribution with mean 0 and variance of sigma squared. Well, variance, we don't know this variance exactly, but let's assume there exists some variance for this. Okay. Then the likelihood, the density function for the normal distribution is this. So density function for data point, not x, but epsilon I is this normal distribution, 2 pi sigma exponential of xi minus, not xi, but epsilon I squared, because the mean is 0, so we just square epsilon I, and 2 sigma squared. So the likelihood function is the product of this, right? F epsilon 1 times f of epsilon 2 times and so on. And if you take the logarithm of this likelihood, it will be something like this: 2 n over 2 log 2 pi minus n over 2 log sigma squared and minus 1 over 2 sum of, so y minus alpha minus beta x I squared over sigma squared. So this part is epsilon I, right? So this is the log likelihood of this problem. So we want to maximize this likelihood, so we differentiate it with respect to alpha and equate it to 0, and differentiate with respect to beta and make it 0, and solve for alpha and beta, and we get the same result because this term doesn't include alpha or beta, and this term doesn't include alpha or beta, so we can just ignore them. And these are just constants, so we can ignore them. Then what's left is the sum of squared difference deviations. So actually maximizing this likelihood, no, so there is a negative sign here. So maximizing this means minimizing the sum of squared errors. So it's just the same problem, and we of course get the same results as this. So alpha is the estimate of, no, this A is the estimate of alpha, and this B is the estimate of beta. Okay. So, and so that's another way to look at the problem. But there's something more. What's nice about this formulation based on maximum likelihood is that it can be shown that this parameter alpha, or A, the estimate of A, estimate A, follows normal distribution. Okay. So this A follows normal distribution with mean alpha with some variance, and also B follows normal distribution with mean beta with some variance. And the variances here can be given as, I don't prove how this can be obtained, but just give you the result. And that's x bar squared over sum of xi x bar squared. So the variance of A is given by this, and the variance of B is given by this. Okay. And also the sum of squared errors divided by sigma squared can be shown to follow chi-square distribution with n minus 2 degrees of freedom. Okay, this s squared is this part. Okay, so this is s squared. Okay. I don't explain why the degrees of freedom is n minus 2, but I think you can get some idea why s squared follows chi-square distribution, right? So let's put small s is equal to large S, so this is same as this one, n minus 2. So let's define this. And so if you define t as b minus beta divided by small s, this one, and times this n x I minus x bar squared. So this follows the t distribution. Okay, follows t distribution with n minus 2 degrees of freedom. Okay, I think you can see that this part, this part comes from this part. Okay, so what was the definition of T statistic? Remember? So T statistic is obtained by the ratio between a random variable following the standard normal distribution divided by some variable that follows chi-square distribution with n degrees of freedom, in this case n minus 2 degrees of freedom, so divided by n minus 2. So that should follow the t distribution. So in this case, this y corresponds to this one, and n minus 2 corresponds to this one, and z here corresponds to, in this case, this B follows the normal distribution with mean beta and variance of VB. So, oh, it's getting messy, but anyway, B minus beta divided by VB. So that's this one, okay? Follows standard normal distribution, 0, 1. So you divide this one by the square root of this one, and this one divided by n minus 2. So that should give you this one. Okay, that's T statistic. Then what this means is that we can apply the t-test to see whether the value of this B is significant or not. So usually our null hypothesis is that the value of this beta is 0. Okay, so this is null hypothesis. So just put, beta equal to 0, so just remove this part and calculate this T statistic. This value can be calculated purely based on the data, right? Although the value of sigma here is assumed initially, but in order to calculate the T statistic, we don't need this value of sigma. So this T statistic can be calculated based purely on the data. So just the data in this case means the pairs of x and y's, x1, x2, y2, and xn, yn. Okay, just using this data, you can calculate this T statistic and test the null hypothesis that beta is equal to 0. If that's significant, then that means the value of this B, it's significant, which means if beta is 0, then what we get is a line like this. It's a horizontal line, right? Not something like this. So when B is significant, that means this slope is significant. It's significantly different from this horizontal line. Okay, so that means the data, we get here like this. It's not random. So it has some tendency that varies linearly along with this line. And of course, you can test the value of A in a similar manner, and you should try to find the T statistic for testing A.